This video is sponsored by PCBWay. Hey there, this is Seth Schaefer from Team Just Cuz Robotics, and this is a prototype of the newest robot that I've been working on for the last several months. I'm excited to finally do a design overview today, talking about all of the little design decisions that went into this and the component choices. And I'll also be giving an overview of the actual CAD design for it and explaining my design decisions and different choices that I made in picking components. Plus, I'll give a little bit of information as to how I go about the process of designing a robot in the computer to make my life easier when actually building it in real life and prototyping, and also how to make a parametric design so that you can make quick adjustments to your model without destroying the entire thing in the process. That's something that a lot of beginners struggle with when they first get started in CAD. It's a little bit more of an advanced technique, but it is a game changer when you can get it to work correctly. Now, first things first though, I also am going to be talking about this little guy right here, which is actually one of these. It is a motherboard, Just Cuz Motherboard, which I developed specifically for this robot and other robots like it. Robots that have a powerful servo lifter, such as you see here, and they allow you to run your servo even if it's only rated for up to 8 volts, or even as low as 5 volts with a battery up to 36 volts. So I think that might be really useful for a lot of bot builders who are making servo bots. And it also has an integrated receiver right on the board, which you can't really see because it's covered by wires, to make your wiring as compact as physically possible. So it doesn't need to be used for a servo bot, but really for any robot at all that you want as tight and compact wiring as you can have. To start out with, why exactly did I design a lifter control bot in the first place? Well, I've had a number of people over the last few months asking me, hey Seth, you started selling these drive motors on your web store and you're saying that they're really light and really powerful and great for Beetleweights. So why aren't you using them in your own robots? Well, the obvious answer to that is simply that I only started selling them relatively recently. They've only been around for like a year and change at this point. And I had already designed the latest version of Division with my custom brushless drive solution that I use on that bot prior to when Dartbox even became a thing. And Shrapnel Mine I had already had existing from a year prior to that, and I only refreshed the design in a few ways when I brought it to most recent competition in Labor Day Disarray. And so I couldn't change the drive system from what Shrapnel Mine was using to something completely different because the robot was too narrow for me to fit 2 Dartbox motors side by side. This robot, however, I wanted to show the power that Dartbox motors can provide. And not just that, but I figured I may as well go all the way and just use as many of my own store's components as possible in it. So right now, I don't actually have a name for this robot. Make sure to comment down below what you think its name should be, but the working name I have for it right now is SSP, which was kind of a joke that I've told a few people, that I would call this robot shameless self-promotion, since, you know, people accuse me of talking about my products all the time in Discord and Facebook and whatever because I don't pay for advertising, so that's the only way I can get advertising for them, other than this YouTube channel, of course. So let's pull back the curtain here and take a look under the lid on this bot. So you'll see here at the heart of the robot are 2 Dartbox drive motors. Now I sell 2 versions of this on my web store. There's the Viper and the Dragon. The Viper motor is really powerful and the Dragon motor is 50% more torque than that, but the same speed. Right now, my test platform, I'm testing using early samples of the Dragon motors, and it has an absolutely stupid amount of pushing power. So I might actually step down to the Vipers just because the Dragon motors tend to run a little bit warmer and they're a little bit less energy efficient. But frankly, the battery in here is already super overkill and it lasts for like 20 minutes of driving around anyway, so I might just leave them as is. why did I choose to use the Dartbox motors? I already talked about that because they work really well. But I also found that by just belting one wheel to the other, I can get a really good compact four-wheel drive solution with these. And this is one of the reasons that I actually got these custom gearboxes made with an extra long shaft, specifically so that it makes it easy to do exactly what I'm doing here, where you can have a belt that is connected to the wheel hub on one wheel and just belt it all the way over to the other wheel. Now, to actually drive the wheel, I'm using my own 12mm hex hubs. You can actually see if I dig down deep enough here. These are just Cuz Robotics 12mm hex hubs with a 4mm bore. Now, you do actually have to modify them to do this because by default, they actually have like a thread for an M4 screw, so it's smaller than a 4mm bore, but I just ran a 4mm drill bit through it. It takes like 2 seconds, and all of a sudden you can put it all the way down the shaft however far you want. And then if I hide the belts here, you can see that you can just clamp them to the shaft with set screws that are into the aluminum hub. Set screws don't really work in 3D printed plastic, which is why you can't just make a 3D printed wheel hub have the set screw in it to hold to the shaft. It'll just slip. I've tried it before, it doesn't work at all. So I'm using my Just Cuz hubs, I'm using Just Cuz Dartbox gear motors, I'm doing custom cast urethane wheels like I've done on all of my bots recently. That I have a whole tutorial video on, you can check out at the card up here, hopefully. And then we've got the motherboard, which I designed specifically to make use of a powerful servo in this robot. Now you might be wondering, hey Seth, you sell a high reduction version of the Dartbox gear motor. Why wouldn't you just use that to power the arm? The answer is twofold. Number one is cost. I can get these servos in bulk for like 10 or 20 bucks each, and they're really powerful and actually deliver even more torque than a Dartbox gear motor because they actually have a higher internal reduction. Number two is complexity. I would need to have a separate third speed controller in here because I already have 2 speed controllers through the Terracan essentially, which is a dual brushed motor speed controller that I sell on my web store. This Terracan can run 2 drive motors on 2 independent channels, but it cannot run a third motor for a lifter independent of those. Although if you decided for some reason that you wanted 4 drive motors, you can actually drive 2 on each channel of the Terracan if you're using the Viper motor. Dragon motor is a little bit too much peak current draw, so I wouldn't recommend running 2 Dragon motors off of one channel of the Terracan, but 2 Viper motors should be fine. So the servo, it's really compact. It's much shorter than the high reduction gearbox. As you can see, the high reduction gearbox would actually be a little bit longer than this whole Dartbox motor here. So it's a lot shorter and more compact because of the compact gear stage that's already built into the servo. And on top of that, it has positional control because it's a servo. So you just plug that servo right into channel 3 pins on the motherboard, and all of a sudden you have angular control of the arm. That means instead of with a continuous spinning motor, when you push the stick up, it just starts spinning, and when you push the stick down, it starts spinning the other way, but there's no way to tell it what angle you want to go to. With this, I can push the stick to a particular angle, and the servo will go to that angle and stay there. And then if I change the stick position, it'll go to that other angle and stay there. I push it all the way, it can go basically 180 degrees back and stay there. I don't have to worry about the motor stalling out when I hit my own frame or anything crazy like that. So that's why I'm using a servo. And I designed the motherboard in tandem with the start of the design of this robot, specifically to make the best use possible out of a servo. This little daughter board on the motherboard right here, and yes, that is an actual electrical engineering term, daughter board is a BEC essentially, but it is a really fancy, nice BEC. Here is an example of what I'm talking about on a motherboard itself. So this regulator board here does a couple things very differently from the one that is on the all-in-one PD board that I also sell. The all-in-one PD board has a BEC on it as well, but that BEC is rated for 1/2 amp of current at 5 volts, and it can only produce 5 volts. Now, if you look closely, you'll see I labeled one of these pins on the bottom trim. That's because this regulator on top of being rated for 3 amps instead of half of an amp, it has a trim function that lets you change the output voltage to something higher, or actually even a little bit lower, but I only have it configured to go higher than the typical output voltage. There are some other regulators that allow you to do this, but usually they create unstable voltage ripple when you go to something above like 25% above their rating. But this guy I've tested producing 8.4 volts from a standard output voltage of 5 volts, and it works flawlessly. I can stall servos to the point where the servo motor actually blows up and the servo dies without this guy overheating. It's phenomenal. However, not every receiver can survive a higher voltage. So you can see I designed around using the FS2A receiver, which is a really commonly used tiny receiver in Antweights and Beetleweights because it's like 4 channels and it weighs like 2 grams. So you can actually slap that on here, solder it directly to the board, and that receiver can take up to 10 volts with no problem. If for some reason you actually want to use a different receiver though that only operates at 5 volts like most receivers do, or pretty much every receiver does, that's okay. Down here at the bottom, there's a little thing that says SB, and there's a solder bead next to it. SB stands for solder bridge. So by default, this will come without that solder bridge in place, and it will output 5 volts from the BEC. You simply put a tack of solder on there and bridge that, and it connects the resistor to the trim pin on the regulator, creating 8.4 volts instead of 5 volts from the regulator. And then you need to be using something like the FS2A or a different compatible receiver that can take up to 8.4 volts. And you'll be able to run a servo at 8.4 volts, getting way more torque and power out of it than you would get at 5 volts. So basically, long-winded way of saying, the motherboard lets me get the absolute peak performance possible out of a servo, and I don't need to have a separate extra BEC because the motherboard has it on it, and I don't need to have a separate battery to run on 2S just for the servo and 3S for the rest of the drive system, because the regulator takes care of it, and I get the receiver built right into it without any extra wires. So it's incredibly convenient and compact. While we're talking about this motherboard, which is a PCB, I may as well talk about today's video sponsor, PCBWay. PCBWay is a fabrication service for PCBs, CNC machining, and 3D printing operating out of Shenzhen, China, and they have been a longtime sponsor of my channel for now just over a full year. PCBWay's been working with me to help me when I need really quick turn prototypes of boards like this, and they also have made some CNC machine parts like the chassis for my Beetleweight division and a number of other things on other bots in the last year or so. I wholeheartedly recommend their service. Every time I've used them, they've been great. For PCBs, when you're getting bare boards, they're super fast and super cheap. I would definitely recommend checking them out if you are a PCB designer and you need any boards made in the near future. And if you're interested in getting parts CNC machined out of metal, plastic, you name it, you should definitely check them out as well. Check out PCBWay.com at the link below, and you can get $5 off of your first order through referral through that link. Inside of SSP, got like Dartbox drive motors for drive. I've got the Terracan to power them. The battery that I chose right now is a 450 milliamp hour 3S Ovonic, but I might be able to use a Tatu battery as well. That is a really, really low cost option. It's 3 cells and it's not gigantic. That's pretty much the only reason I chose it. In theory, pretty much any 3S battery or 4S battery in theory would work. The motherboard can regulate whatever voltage I would feed it down for the servo. So it's just a matter of what I'm trying out. For right now, I'm running 3S because the Dragon motors can run a little bit hot, but if I switch to the Vipers, I might actually start running on 4S because I was testing with both the Dragon and Viper motors on 4S already. They seem like they can, in fact, handle it. I had originally been skeptical that the Dragon motors might get too hot, but in my testing so far, that's not really been the case as long as you provide enough ventilation for them. So you can see in the lid here, I added some vents so that there isn't like absolutely no cooling, though of course there's this big chasm where the servo arm would go that probably helps a little bit while the robot's driving forward, getting some forced air in there. If you have complete closed chassis and you're running these brushed motors, they do tend to get a little bit toasty, so you should make sure to add ventilation where needed. So let's start talking about the actual physical design features of the robot. You might notice that there's some weird spiky things going on the wheels. That's because I actually have 2 different wheel options. I've got these spike wheel cleat type things that have been popular at Norwalk that I might try out for this, but I also want to have the option to switch back to a traditional molded urethane tire. The urethane wheel is definitely going to be heavier, and it will probably provide a little bit less grip. However, it also is, the devil I know. And when I was running Shrapnel Mine at the most recent competition in Labor Day's Array, their floor just got chewed up by the spike wheel prototypes I made for that, and I didn't get any traction at all with them. So even though I definitely will have urethane on the back wheels to make sure I get at least some traction, these front wheels are going to be carrying the vast majority of the weight of the robot. This little circle thing right here is actually the center of mass of the robot, and you can see it's just behind where the front wheels touch the ground. So making absolutely certain that I have functioning front wheels is a major priority, and that's why I might just run with urethane on both. I also did a test earlier, which I might show a clip of here if I have it recorded properly, where I put 3-pound weight on top of the chassis that I had been running, because the chassis by itself with just the electronics is like just over 1.5 pounds and wouldn't get enough traction otherwise. I was able to push 19 pounds worth of water jugs across the floor of my apartment just using 4 30A silicone cast wheels. So I don't think that I will need the extra traction from cleats. Now, the other risk of cleats is if an undercutter hits them and they get bent up, they could bind up everything, whereas the urethane tires will probably just chunk away and that won't be a huge deal. Let's talk a bit more about offense. We've got this arm, which right now I have mocked up as being 3D printed out of TPU, and then some AR500 little forks that get bolted on. I am using these shoulder bolts in a lot of places. I've color-coded some of the screws that I use most often, so you can see I made an effort to use as few different fasteners as possible. And there's these blue, these are 1/2-inch flathead number 6 plastite screws that are used most frequently everywhere, including on the lid. And then we've got in green, these are 35 millimeter long, 4 millimeter diameter shoulder bolts. And then I use those for supporting the front drive wheels as a dead axle. And I have actually one even supporting the lifting arm on the side, so that if something hits this, especially like a horizontal spinner hits this, it won't just completely annihilate all the gears inside of the servo. Now, I've also got this interesting feature for the front attachments that are called dovetails. Dovetails are frequently used in wood joinery, but they are actually pretty interesting and useful in metalworking as well, because you can make a nice, precise, slotted interface that fits tightly and you can't pull it out, but it doesn't require extra screws. Now, the reason that I'm using dovetails is twofold. Number one, it reduces part count by meaning I don't need any extra screws to fasten forks and wedges and whatever else onto the front of the robot. And number two, this chassis design is not actually meant to be 3D printed. Like, obviously I 3D printed the prototypes, but the intent behind this chassis is to do exactly what I did with Division and make it a solid billet chassis that's machined out of a single block of material. In this case, let me show you exactly what only the chassis itself looks like. So I'm going to isolate this here. And you can see from a top-down perspective, you'll notice there are a lot of radiuses everywhere. And that's because when you're machining, you have an end mill with a fixed radius that's coming down from the top to make all of these features. I wanted to make this chassis as cheap and easy to manufacture as possible. So I used a large internal radius, which means you can use a bigger tool that removes material faster to make the whole machining operation take less time. And having these generous internal corners everywhere means that you could use up to 1/4 inch or even maybe 7 millimeter end mill to machine out all of these features. And because it's not a 5-axis design, it's just like a 3+2 design where you've got a couple features on the side and from the top, and other than some countersinking, there's basically no features that need to be done from the bottom. There will not be a huge number of setups, which also helps to reduce the cost for making the part. You will notice, however, I've got this weird cutout in the back. The reason for that is because I wanted the wheels to be able to touch the ground even if the front of the robot gets propped up because another robot's wedged underneath the front of mine, So let me unisolate everything so you can see what I'm talking about. So you can see here, the wheels at the back, this corner would come past where the wheel is, like it kind of does with the lid here. And that would mean that I could lose any traction with the back wheels if the front wheels were lifted off the ground at the worst possible angle. So this dovetail here, or this cutout here, is actually meant to be made with a dovetail cutter, which is the type of end mill that actually flares out so that you can cut something that's normally impossible to do from the top side. So that can still be done from the top with just a special fancy end mill. All right, I think that covers most of the basic mechanical design stuff. Let's talk a little bit more about the layout and whatnot. So if we look underneath the lid here, I've got the Terracan, I've got a battery, and they're kind of stacked on top of each other. In my prototype right now, I just have them taped together, and then I Velcroed the battery to the bottom of the chassis. I'm still trying to decide if I want to add some sort of bump outs in the chassis to hold the battery in place like I have for the motors and for the servo. But I don't necessarily want to be stuck using only exactly this one battery ever. The motherboard is screwed down. I designed it specifically to take number 6 plastite screws in the corners to hold it down. So I've got little bosses on the chassis to make it thicker there, and I can take a 1/4 inch plastite and just hold it down that way. And I've got a nice screw access switch hole in the bottom, which I'll probably have to countersink this side myself so it doesn't have to be done from the bottom. But this is just a hole that can be drilled from the top, and then you've got access to the screw to turn it on. Now, one interesting thing I'm doing here, you'll see, is I've got these clampy pieces holding components down that are otherwise just secured in pockets in the chassis. That is, again, to reduce the number of screws and fasteners I need to hold everything in, and also to make it way faster to service everything. All I have to do is take out 2 screws. Here's an earlier prototype of the chassis. All I have to do is take out 2 screws, and then motors pull right out, and they are held in very securely. In this chassis, they're a little floppy because this was an earlier prototype, but ideally, they're held in place and not really able to move around much, and they're basically shock loaded by the chassis because it's going to be UHMW, which is a little bit soft, and should not let these just explode when this chassis gets hit. I also know that it's really important to be able to repair within 20 minutes between fights at Norwalk, so having the maximum serviceability and access to components in just a few seconds is paramount. So basically all you have to do to service this robot is take off the lid, take off 2 screws for this motor, 2 screws for this motor, 2 screws for the servo, and you can pop everything out without having to undo any additional hardware. Let's get a little bit into the weeds for the next 10 minutes or so and talk a bit more about parametric modeling and how I made it so that I can make a ton of changes to this design without completely breaking my model, because that's a somewhat difficult thing to accomplish. Now, there's kind of 2 different parts to parametric design that make it possible to make a bunch of changes without having terrible downstream effects. Number 1 is being very, very cognizant about the order in which you actually define things, and number 2 is actually setting up variable names and parameters to define those things. So let me give an example here. This is my list of parameters for this design. It is quite long. You can see there's a ton of names for different things that I could change, and in theory it won't break things, or at least won't break too many things, because there are some things that'll still have enough downstream effects that it causes problems, but the general idea is that I don't have to completely start from scratch if I made the robot a 1/4 inch too wide or something. I'm going to save this now and then make sure that I don't actually break something permanently when I start messing with it, just to show examples of what I'm talking about. So I'm going to set the lid to be 50% opaque so you can see inside and still see the lid updating itself. Let's say I decide that the wheels are too far apart. I want to change the belt length. I actually just did this, so I'm pretty sure this should work to change it back. And let's say I want to change the distance between the 2 wheels from a little over 3 inches to just under 3 inches to use a shorter belt. Now, I just find my parameter for the wheel center distance, and I change it to, say, 2.89, or whatever it needed to be. Hit enter. And now model updates. And boom, the wheels have shifted back along with all of the pockets in the chassis and the lid that went around them. Now you can see there are a few warnings because there's some chamfers that need to be updated, but that's like a super minor thing that takes like 3 seconds to fix. I'm just going to change it back now so that it's the way that I need it for the future. Oh, let's say I decide these forks are too thick and I want to make them thinner. I'll change my static fork thickness to 0.25 and boom, both of those change. Now I can see these little mounts are a little bit too narrow, so I'll change that to 0.7 and those update right away as well. And you can see the screw moves with them and the nuts move with them and everything. Let's say that I think that the lid is a little bit too thin. So I'm going to change my top thickness to say 4 millimeters instead of 2 millimeters. And boom, the lid's now thicker and all the screws moved up with it. I can do a bunch of things like this, even as far as changing like the bottom thickness of the robot. There are some things that are tied to so many things that inevitably it'll start to break stuff if I change too much of it. But there are a lot of things that I can change without completely starting over from scratch and breaking the model. I'm going to undo all of those changes that I just made so that I'm back to where I started. But you can see that I was able to do quite a bit without having to even open up a sketch and change a number manually because I tied them all to these variable names. Now, one of the parts of this design that was tricky to get just right is all of the hugged components like the servo and the motors. Let me give a cutaway view and I can show you what I mean. Of course, my cutaway view is just broke because I messed with the model, but that's okay. So this is basically halfway through the drive shafts of the back of the robot. We can see this is a section view here. You can see like the set screws for the hub going to the shaft and everything. So here I had to make it so that the chassis supports the motors. So I have these raised sections of the chassis that come right up to hug the motor and to come up and hug the gearbox to make it so that the motor isn't just wobbling around separate from the gearbox when there's a big hit on the bottom of the chassis and it tries to fling everything upwards or whatever. To make it so that this would work and I could still change things like the inside height of the chassis and whatnot, I actually defined an inside height variable, and then the gearbox is 16.5 millimeters square. So you can see if I run into my main chassis component and I highlight this guy so you can see exactly where this extrude was that formed it. If I double click on this extrude, you can see I defined it as inside height divided by 2 minus 16.5 millimeters divided by 2. And that just ensures that it comes up to the exact right height to hug the gearbox. And even if I change the inside height of the chassis with that parameter, it will automatically always hug the gearbox. I did something similar for the motor. I just defined that as an offset based on that parameterized value. So for hugging the motor, I just measured and I found that I need 0.078 inches of offset from here. So this extrude command is just a to object. So I'm coming up from the floor to this boss and then offsetting it by the correct amount. I did something similar for the servo. If I switch to the arm stack up here, I basically made it so that since the servo is like 20 millimeters and I wanted a little bit of wiggle room, this guy is arm pivot height, which I defined as a variable, minus 10.2 millimeters, which is about half of the thickness of the servo. So I get this boss that comes up right to the bottom of the servo, and if I decide to change the arm pivot height, then that boss will move with it so that I don't end up with the servo floating too much in midair. It does look like I messed up here though, where there's some interference, so I'll have to fix that in a minute. There are always some things that don't change perfectly when you start messing with stuff, but it makes your life a lot easier and makes it so that there's a lot less that you need to worry about when you do parametric design correctly. Obviously, I'm not a complete pro at it. I messed up here, but there are plenty of examples of where it might take hours and hours and hours to redo tons of work, find every single sketch that affected a different thing that you could save by implementing variable names correctly and always parameterizing the important values in your design. One last thing I want to talk about here is geometry. When designing control, lift, or robot, you have to take into consideration a lot of different factors to make sure it'll actually work correctly. You'll notice these forks are really long. I might be able to make them shorter, but I can't make them too much shorter because if I actually want to lift up another robot, I need to make sure that the front point of contact with the floor that I have is essentially going to be in front of where the center of gravity of that robot and my robot combined would be. Because if I start trying to lift up with my arm here, my robot might just end up tipping forwards rather than allowing me to actually pick something else up. So I have here a little marker that indicates where the center of gravity of the robot is. And that's really helpful for a number of things. Number one, making sure that the center of gravity is behind the front wheels. Otherwise, the whole time the robot's driving, it would just be tilted onto the forks and front wheels, and the back wheels wouldn't be doing anything. Number two is figuring out how I can self-right. Let's say that my robot flips upside down. It is invertible, but now these forks are stuck up in the air and I can't really lift anyone, so it'd be nice to be able to flip right side up again. You'll notice I kind of designed the lifter forks in such a way that they should be able to work right side up or upside down, but if I need to lift somebody up from this orientation, I can only bring them to here. So I'd still like to be able to flip myself over. So if I start moving the arm down at a certain point, I know that I'll be able to tip my robot back onto its wheels because I get to a point where essentially this tip, if the floor is like a line between where this wheel contacts the ground and where this tip is, I need to make sure that this tip and this wheel are touching the floor at the same time when the center of gravity is in front of the point of contact with this wheel, which you can see it is here. And that way I know that the robot will just flop back onto its front. I can bring the arm back down and be on my merry way right side up and not need to drive inverted. If this arm was a little bit too short, I wouldn't be able to do that, and the robot would just flop upside down like a fish, moving the arm back and forth over and over again, and so on and so forth. So that's the main reason why I chose the length for this arm to begin with, to make sure that I can actually flip myself over if I need to. In general, keeping the center of gravity of your robot as low to the ground as possible is usually a good idea. So having the battery on the ground and stacking the speed controller on top of it, rather than vice versa, is both convenient and it helps to promote a lower center of gravity. The drive motors kind of have to be in the middle of the height of the robot, but if you're belting from like one drive motor in the middle to two different wheels, you could bring that motor as low as possible to lower your center of gravity a bit further, and so on and so forth. I think with the amount of pushing power I should have with this, it's not a huge deal to have the center of gravity as low as physically possible, but it is always something that's useful to keep in mind when designing a robot. So, I think that pretty much covers everything I wanted to talk about today. If you have any questions, as always, make sure to leave them in the comments. If you liked this video, make sure to click like, and if you want to see more videos like this and updates on this build as I make progress on it, make sure to subscribe and click the bell icon so you get notified when new videos come out. That's all I've got for today. Thanks for watching.